Hello friends, I welcome you all in the course on Turbo Machine. Today we shall covering Unit 1 topic, that is Introduction to Turbo Machinery. So friends, in the previous session we have discussed prerequisites for a turbo machine subject. So we have discussed basics of fluid mechanics, that is properties of fluids. Then we have discussed some trigonometric formulas and triangle law. So we will start our today's lecture. So fluid machines. So fluid machine is a device exchanging energy, that is work, between a fluid and a mechanical system. Fluid machines are those devices that are used to either move fluid or extract energy from moving fluid. So fluid machines are the rotary machines. So in a particular turbo machine is a device using a rotating mechanical system to perform work or extract energy. So broadly speaking, the fluid machines are divided into two groups: positive displacement machine and turbo machine. These are the two different types of fluid machines. So positive displacement machine, as per the name, so positive displacement machine are those devices that force fluid into confined volume. So the volume is fixed or confined. So this device is known as positive displacement machine. It moves the fluid from maximum to minimum volume and vice versa. So the example of positive displacement machines are human heart, reciprocating pumps and compressor. These are the examples of positive displacement machine. The second type is turbo machine. So turbo machines or turbines are classified as all those devices in which energy is transferred either to or from a continuously flowing fluid by the dynamic action of one or more moving blade rows. So the best example is ceiling fan is the best example of turbo machine. The another examples of turbo machines are Pelton wheel, Francis, Kaplan. These are the examples of turbo machines. Now here you can see that the human heart is the best example of positive displacement machine. Then reciprocating pump is example of positive displacement machine, and ceiling fan is again example of turbo machine. So the next important is introduction to turbo machinery. So friends, turbo machine is basically a rotating machine. It is nothing but a wheel. A rotating wheel is called as rotor, runner or impeller. The rotor will be immersed in a fluid continuum. The flow is continuous. The fluid medium can be a gas, steam, water or air. If the fluid medium is gas, then the turbine is known as gas turbine. If the working medium is steam, then the turbine is known as steam turbine. If working medium is water, then it is known as water turbine. And in a compressor or in a wind turbine, air is used as a fluid medium. So here you can see that a compressor rotor imparts energy to the fluid, and in a turbine the turbine rotor the extract energy from a fluid. So the compressor is a power consuming device and turbine is a power producing device. The another diagram, it shows the steam turbine setup. So you can see that it is fully made up of a alloy steel and it is super finished and it's complicated. The next is definition of turbo machine. So the turbo or turbines is of Latin origin and it implies that which spin or whirl around. So the turbo is a turbo word is have the Latin origin and it implies or its meaning is spin or whirl around. The turbo machine is a rotary machine which always involve an energy transfer between a continuously flowing fluid and a rotor. So the turbo machine is an open type of system. So fluid enter and it leaves. It is a power or head generating machine. It uses the dynamic action of the rotor or impeller or runner, which changes the energy level of the continuously flowing fluid through the rotor. The turbo machine is a device where mechanical energy in the form of shaft work is transferred either to or from continuously flowing fluid by the dynamic action of rotating blades row. So blades may be one or more moving blades rows are used. So normally water turbine have the single moving blades, but in a steam turbine more number of moving blades are used. The interaction between the fluid and the turbo machine blades are also results in fluid dynamic lift. So here is some examples of different types of turbine. So this is nothing but a Francis turbine, Pelton wheel, fixed pitch propeller, Kaplan turbine, then cross flow turbine and turbo turbine. So in the next session we will discuss Pelton turbine, and unit number third is based on a Kaplan, Francis and propeller turbine. So the next important point is classification of turbo machine. So the turbines can be classified according to the various criteria, but the basic two criteria is power producing and power absorbing. So here you can see that the general schematic arrangement for hydraulic turbine and centrifugal pump. In a hydraulic turbine, the energy is produced. So the name tells us the power producing, and in a centrifugal pump, power is absorbed. So the high energy, the fluid with high energy enter in a rotor. The turbine extract the energy and it producing the shaft work, mechanical work, and the low energy fluid exists from a rotor. But in a pump, we have to supply some external work, that is electricity. So impeller rotates and it extract the fluid with low energy, and the impeller work is supplied to the fluid and we will get a high energy fluid. So it is a basic arrangement for a turbine and a centrifugal pump. Again here you can see that the different examples of power absorbing machine and power producing turbo machines. So fan is example of turbo machine. So in a fan, air is the working medium and it is axial flow type and radial flow also, as well as centrifugal flow fans are available. Blower, air is the working medium and the flow arrangement is axial flow, radial flow as well as centrifugal flow. The next example is propeller and ducted fan. So ducted fans are used in ducts, in refrigeration air conditioning ducts. So in this case, air is used as a working medium. Then the compressor, in a compressor, air is used as a working medium. The reciprocating compressor, rotary compressor, axial flow, radial flow and mixed flow, these are the different subtypes of compressor. The next example is pump. So all these fan, blower, propeller, compressor, pumps, these are the power absorbing machine. The power is required. The pump, in a pump, water is the working medium. Again in a pump, reciprocating pumps, axial flow pumps and radial flow pumps or mixed flow pumps are used. In a power producing turbo machine, gas turbine, steam turbine, hydraulic turbine and wind turbine, these are the different examples of power producing turbo machine. So in a gas turbine, air and combustion gas is the working medium. Again in a gas turbine, axial flow and radial flow type of gas turbines are used. Steam turbine, again as per the name, in a steam turbine, steam is the working medium. Hydraulic turbine, water is working medium. Again in a hydraulic turbine, impulse, reaction, mixed flow and axial flow types of turbines are used. Wind turbine, in a wind turbine, air or wind is the working medium. Again it is a vertical axis type and horizontal axis type windmills are used. The next important point is classification of turbo machine. So friends, the turbo machines can be classified according to the various criteria. So we will discuss one by one. So the first criteria is based on energy transfer. So energy is given by fluid to the rotor. So fluid supplied energy to the rotor. So it is nothing but a turbine. So power generating turbo machine is example of turbine. The energy given by rotor to the fluid, it is power absorbing machine, power absorbing turbo machine, and the example is pump, blower and a compressor. So based on energy transfer, energy given to fluid to the rotor and energy given by rotor to fluid. These are the two subtypes. The next is based on fluid flowing in a turbo machine. So water, air, steam, hot gas, liquids like petrol, these are the different working medium. And we know that if water is a flowing fluid, then the turbine is known as water turbine. If air is a working medium, then windmill or wind turbine is a example. Steam turbine. Hot gas, it is gas turbine. The next classification is based on direction of flow through the impeller or vane. So based on direction of flow means what? The fluid direction through rotor. So it is classified into four subtypes: axial flow, mixed flow, radial flow, and tangential flow. If the fluid flow is along, its direction is along the axis of the turbine, then the turbine is known as, or pump is known as axial flow, axial pump, and compressor or turbine. Mixed flow. So mixed flow pump and Francis turbine is example of mixed flow. Mixed flow means what? The flow direction is axial as well as radial. Then this type of device is known as mixed flow type of device. Radial flow. If the direction of flow is along the radius of the rotor, then the device is known as radial flow device. Example is centrifugal pump or compressor. And tangential flow. If the flow direction is along the tangential of the wheel, then the turbine or device is known as tangential flow machine. And the example is Pelton water turbine. Pelton water turbine is a impulse type of turbine. The next classification or criteria is based on condition of fluid in a turbo machine. So there are two subtype: impulse type and reaction type. So in impulse type, the pressure remains same. The example is Pelton water turbine. And the reaction turbine, the variable pressure. The pressure changes from inlet to outlet. So this type of arrangement is known as reaction type. And the example is Francis turbine, propeller, couplant. These are the examples of reaction turbine. The next criteria is based on position of rotating shaft. If the shaft position is horizontal, vertical, inclined, so mostly horizontal and vertical type of shafts are used. Shaft arrangement is used. So horizontal shaft turbine is a steam turbine. Vertical shaft type of turbine is couplant water turbine, and inclined shaft is a modern bulb micro hydro turbine. These are the advanced turbine. The next point is comparison of turbo machine with positive displacement machine. So the difference is simple. So we will discuss one by one. So turbo machine and positive displacement machine the difference is here. So turbo machine, it creates the thermodynamics and dynamic action, rotating element and flowing fluid energy transfer takes place if pressure and momentum changes. In a positive displacement machine, it creates thermodynamic and mechanical action between moving member and static fluid, and energy transfer takes place with displacement of fluid. The second difference is it involves a steady flow of fluid and rotating motion of mechanical element. In a positive displacement machine, it involves unsteady flow of fluid and reciprocating motion. It operates at high rotational speed because turbo machine is a balanced type of machine, but in a positive displacement machine, they operate at low speed because positive displacement machines are unbalanced type of machine. Change of phase during fluid flow causes serious problem in a turbo machine. For example, in a steam turbine, if the steam is condensed, then it causes a serious problem in a steam turbine. But in a positive displacement machine, change of phase during fluid flow causes less problem in positive displacement machine. The efficiency is usually less. Efficiency is higher for positive displacement machine. It is simple in design because balanced type of machine. It is complex in design. Due to rotary motion, vibration problems are less. Already we have discussed, it is a balanced type of machine. So due to balanced type of machine, there is no vibration or the vibrations are less. Due to reciprocating motion, vibration problems are more. And the examples of turbo machines are hydraulic turbine, gas turbine, steam turbine, windmill. These are the examples of turbo machine. In positive displacement machine, IC engine, reciprocating air compressor, pumps, these are the examples of positive displacement machine. Again, some points related to comparison between turbo machine and positive displacement machine. It generally has rotary motion, turbo machine, and positive displacement machines are generally it involve reciprocating motion, very high operating speed is low, weight per unit power output is low, weight per unit power output is large. Vibration free operation, it occurs with vibration problem. No walls are present. Yes, it is a main important difference. Walls are employed or present, that is inlet wall and outlet wall. Suction discharge walls are present. Then the suitable for large volume flow rate of fluid with high velocity, suitable for smaller flow rate of fluid with limited velocity. uh, Turbo machine, that is axial and centrifugal compressor, are used where large volume of flow rate is required, but reciprocating compressor gives the small flow rate and limited velocity. Turbo machines are less efficient, and positive displacement machine have the higher efficiency can be achieved. Volumetric efficiency is more. Less volumetric efficiency we will get by using a positive displacement machine. The next important point is application of turbo machine. So turbines are used in hydro, steam, gas. So hydroelectric turbine or turbo machinery uses potential energy stored in water to flow over open impeller to turn a generator which creates electricity. Steam turbine. In a steam turbine, use in a power generation, and the overall principle is high pressure steam is forced over a blade attached to the shaft which turns a generator. Gas turbine. In a gas turbine, uses a hot gas. The air is forced through a series of blades that turn a shaft. Then the fuel is mixed with the air and causes combustion reaction. This causes shaft to spin faster and creating the more electricity. The next application is windmill, turbocharger, supercharger, pump, air compressor, fan. Again, fan is the most general type of turbo machine. They work opposite of wind turbine, because wind turbine is a power producing device and fan is a power absorbing machine. Mechanical power spin the blades and forcing air through them and forcing out. The next important point is losses of steam turbine or losses of turbo machine. Losses of turbo machines are classified into two types: internal and external losses. The internal losses, as per the name, the losses occurred in the internal side of the turbine is considered as internal losses. So the losses which takes place in the inner passage of the machine and directly connected with rotor or flow of the medium, and which are adding heat to the flow medium. The internal losses of the machine occurring in the casing and impeller are referred to as hydraulic losses. Due to inner losses, the total energy exchange between the rotor and the flow medium is changes or decreases. The losses can be specific energy loss and volume mass flow loss are considered as internal losses. External losses are losses which appears outside of the inner passage of the casing and which do not transfer the generated heat directly into the flow medium. All external losses due to friction in the bearing, sealing, and due to the fluid friction at the outside rotating surface of the machine can be counted together as a power loss. The external loss also include loss from auxiliary equipment, oil pump, bearing, lubrication, speed regulator. These are the external losses. The frictional and other losses. The effect of these losses is to reduce the stagnation pressure and increase the entropy. If the losses are occurred, the entropy value increases. Reduce the net work output in a power generating machine and increase the net work input in a power absorbing machine. So we have to minimize the losses, that is internal losses, external losses, and frictional losses. So the first frictional loss is this friction loss. The surface of the rotor which does not form the main flow passage is surrounded by a fluid medium. While the rotor rotates, a friction is generated between rotor surface and its surrounding fluid medium. The hydraulic loss. The hydraulic loss is a specific energy loss due to friction, separation, contraction, diffusion, eddies formation, and while the flow passage through the main flow passage from entrance to discharge flange of the machine. Hydraulic losses we have already discussed in fluid mechanics, that is major loss and minor loss. Then the leakage loss. In case of impulse turbine, whole of the water may not be striking the buckets and therefore some of the water power may go to waste. In a reaction turbine, some of the water may be passing through the clearance between the casing and runner without striking the blade and thus not doing any work. The leakage losses, in a leakage losses, uh, the water the water passing through the clearance between the casing and runner, and these losses are considered as leakage losses. The next loss is mechanical loss. As per the name, the mechanical loss is due to the loss takes place in a bearing friction, and the power produced by the runner is not available as useful work of the shaft because some power may be lost in bearing friction as a mechanical loss. Generator loss. It is related to electrical engineering. Due to generator loss, power produced by the generator is still lesser than the power obtained at the turbine output shaft. The next important point is fundamental equation or governing equation for turbo machine. So basic laws of fluid mechanics and thermodynamics used in a turbo machinery or turbo machines are equation of continuity, it is law of conservation of mass, then the first law of thermodynamics, second law of thermodynamics, Newton's second law of motion, Newton's third law of motion, Euler's equation and Bernoulli's equation. These are the basic laws are used in a turbo machine, and the whole turbo machine subject is based on Newton's second law of motion and Newton's third law of motion. So we will discuss one by one. The first law, basic law, is equation of continuity. It is also known as law of conservation of mass. So we know that mass cannot be created nor be destroyed. Similarly, continuity equations state that the rate at which mass enter a system is equal to the rate at which mass leaves the system plus accumulation of mass within the system. The another statement for continuity equation is this law states that in absence of source and sinks, there is no accumulation of fluid within the control volume. And the mathematical statement is simple. So mass flow, it is m dot. M dot is equal to rho v a, that is rho into q. Rho is the density of fluid, v is a velocity, and a is the cross section area. So at different section, the mass flow rate remains same. So if you take a section at different levels, we will get the same mass flow rate at different section. So we can write down this equation like that: rho 1 v1 a1, rho 2 v2 a2, and density remains same. If the fluid is incompressible, that at that time the density value remains same. So vn and an, these are the n values. The next law is first law of thermodynamics. It is known as internal energy law. The first law of thermodynamics is an expression of the conservation of total energy of the system. That is, law of conservation of energy is nothing but the first law of thermodynamics. The increase of the energy of a system is equal to the sum of work done on a system and the heat added to that system. The first law of thermodynamics states that if a system is taken through a complete cycle during which heat is supplied and work is done, so cyclic integral of del q minus del w is equal to 0. So the work and heat is mutually convertible. So if you supply the heat convert into the full amount of work. If you supply the work, we will get a full amount of heat. So the cyclic integral of del q represents the heat supplied to the system during the cycle, and cyclic integral of del w is nothing but work done by the system during the cycle. So during the change of a state from 1 to 2, there is change in the property, internal energy, and the law is written as energy at 2 minus energy at 1 is equal to the cyclic integral from 1 to 2, it is del q minus del w, and the remaining is the internal energy. The next important law is second law of thermodynamics. This the law have the two statements, Clausius statement and Kelvin Planck statement. The second law of thermodynamics introduce a concept of entropy. The inequality of Clausius states that for a system passing through a cycle involving heat exchanges, where dq is the element of heat transfer to the system at an absolute temperature T, and if all the processes in the cycle are reversible, then this equation is applicable, that is cyclic integral of dq by T is less than 0 or equal to 0. The equality holds true for reversible flow only, and the property called entropy for a finite change of state is then defined as by using this equation. And entropy is nothing but a molecular disorderness. So S2 is entropy and after the process, and S1 is a entry side entropy, and the equation for entropy is here. The next law is momentum equation, that is also known as Newton's second law of motion. So one of the most fundamental and valuable principle in machines mechanics is Newton's second law of motion. The momentum equation relates the sum of external forces acting on fluid element to its acceleration or to the rate of change of momentum in a direction of the resultant external force. So rate of change of momentum is proportional to the applied force or external force. The study of turbomachine many applications of the momentum equation can be found. So in a turbo machine subject, the Newton's second law of motion is mostly used. The example is force exerted upon blade in a compressor or turbine is the best example of Newton's second law of motion. The next equation is Euler's equation of motion. So friends, Euler's equation we have discussed in fluid mechanics, unit number 3rd, fluid dynamics. So this equation, the Euler's equation, in which the force due to gravity and pressure are taken into consideration. So this is derived by considering the motion of fluid element along the streamline. So consider a streamline or stream tube. Its cross section area is dA and length is ds. Okay. Then for Euler's equation, we are considering only gravity force and pressure force. So it can be shown for a steady flow of fluid through an elementary control volume that in absence of all the shear forces, the relation is 1 by rho del P plus velocity dV plus G dz is equal to 0. The Euler's equation of motion for one-dimensional flow is derived from Newton's second law, that is F is equal to ma, and the basic generalized equation also we have discussed in a fluid mechanics. So when the fluid is flowing through the pipeline or any system, the different forces are involving. So these forces are Fg, it is a gravity force, Fp is a pressure force, Fe is a force due to viscosity, Ft is a force due to turbulence, Fc it is force due to the compressibility. So from Newton's second law of motion, summation F is equal to mass into acceleration. So summation of F is addition of all these 6 forces, that is gravity, pressure, viscosity, turbulence and compressibility. So friends, Reynolds equation, in a Reynolds equation we consider the 4 forces, that is gravitational force, pressure force, viscous force and turbulence force. In Navier equation we consider only 3 forces, that is gravitational force, pressure force and viscous force, and in Euler's equation we consider only 2 forces, that is gravitational force and pressure force. So you can see that a stream tube at section 1 fluid is enter and through section 2 fluid exists, the density remains same. The next law is Bernoulli's equation. So Bernoulli's equation is also known as energy equation. So Bernoulli's theorem or equation states that the sum of potential energy, that is kinetic energy, pressure energy per unit mass of a liquid, is constant at all section in an incompressible liquid that has a streamlined flow and does not offer any friction or has zero viscosity. If the ideal fluid flowing through the system, then the total energy, that is P by rho g V square by 2g plus Z is equal to constant. So from we can derive the Bernoulli's equation from Euler's equation. So Bernoulli's equation is obtained by integrating the Euler's equation of motion, and friends, we know the Euler's equation, it is del P divided by P plus V dV plus G dZ is equal to 0. Just take an integration on both sides, we will get integration of del P by rho plus V dV plus integration of G dZ is equal to 0. Integration of 0 is constant. So P by rho plus V square by 2 plus Gz is equal to 0. Now divide by G from both sides. So we will get P by rho g plus V square by 2g plus Z, because Gz divided by Gg get cancelled. So we will get Z value is equal to constant. Constant by G is again constant. So from this equation, we can calculate energy at different section. So the P by rho g is a pressure head value. Its unit is in meter. Again V square by 2g is a kinetic head or kinetic energy head, and Z is a potential or elevation head. So the Bernoulli's equation is a energy equation, and the total energy, that is pressure head energy, velocity head energy, and elevation or potential head energy remains constant. And friends, thank you for watching this video. So please prepare a notes on this topic. Thank you.